kinetic and thermodynamic products of conjugated dienes. We know that when conjugated dienes undergo electrophilic addition reactions, it has the ability to form two different products. One is the 1,2 addition product, also called as the kinetic product, which is the fastest product that is obtained, and the other one is the 1,4 addition product. Now, which of these two products are obtained in major amounts? That's going to depend on two important factors. One is the structure of the starting material, and the other one is the temperature. These are the two things that's going to decide which of these products will be obtained as a major product. Now, in general, if the reaction is irreversible, then kinetic product predominates, whereas if the reaction is reversible, then the thermodynamic product predominates. For example, here are two different reactions, and both of them have exactly the same reactants to start with, and even the electrophilic reagents are exactly the same. Here, when the reaction has been conducted at minus 80 degrees Celsius, the kinetic product predominates. Whereas, when the reaction is conducted at a high temperature or comparatively high temperature of 45 degrees Celsius, the thermodynamic product predominates. What is the reason why the kinetic product is favored at low temperature and thermodynamic product is favored at high temperatures? Let's use the reaction coordinate diagram to see why different products predominate at different reaction conditions. Now, whether it is a 1,2 addition reaction or 1,4 addition reaction, the first step is essentially the same in both of these reactions, where it forms the carbocation. It is basically the second step which is going to determine whether the bromine will be added to the second carbon or the fourth carbon. Let's say you're going to conduct the reaction at low temperatures of close to minus 80 degrees Celsius. Now, at that temperature, the reaction has got sufficient energy to overcome the energy barrier of the first reaction, and it forms the intermediate, and it has got enough energy to overcome the energy barrier of the second reaction, and then finally forms the kinetic product. But it does not have enough energy to do the reverse reaction, since there is a large energy difference between the intermediate and the product. Now, let's say you're going to conduct the reaction at a high temperature of 45 degrees Celsius, relatively high temperature. Here, there is enough energy for the products to revert back to the intermediate. When compared to the 1,4 addition product, it will be easier for the 1,2 addition product to revert back to the intermediate, since the energy difference here is small. Once it forms the intermediate, it can decide whether it needs to form the kinetic product or the thermodynamic product. But every time the kinetic product reverts back to the intermediate, more and more of the thermodynamic products are formed. So at high temperatures, it will be the thermodynamic product or the 1,4 addition product which will be formed as the major product. So at high temperatures, 1,4 addition product, and at low temperatures, it is the kinetic product. What is the reason why the 1,2 product is always the kinetic product, or it is the product that is formed faster? Chemists did some experiments where they switched the HCl with DCl to see where the hydrogen is going. So here D represents deuterium, which is a heavier isotope of hydrogen. When they conducted the reaction at minus 78 degrees Celsius, they again were able to get 1,2 addition product as the major product. From the results obtained, they were able to confirm the only reason why deuterium and the chloride ion is getting added to the neighboring carbons, that is at the 1 and the 2 position, because they are closer to each other. Say, for example, when you take this diene, the first thing that's going to happen is these electrons from the double bond, from the pi bond, is going to make a nucleophilic attack on D and thrust these electrons into Cl. Now, as this Cl leaves, it's not going to go far away from this D, right? It's going to stay close to each other. And therefore, since you have a carbocation here, it will go directly, easily attack this carbocation and form the product. That is the reason why 1,2 addition is formed as the kinetic product, which is the product that is formed faster. Although we now know that the 1,2 addition product is always the kinetic product, we cannot simply assume that 1,4 addition product is always the thermodynamic product. Here is an example. Here we have 4-methyl-1,3-pentadiene. When it undergoes an electrophilic addition reaction, it forms two different products. Here is the 1,2 addition product, and this is the 1,4 addition product. Okay, now let's take a look into the stabilities of the two different alkenes. The 1,2 addition product right here is a tri-substituted alkene, right? So it looks more like this. But the 1,4 addition product is a di-substituted alkene, which looks like this. Between these two alkenes, which one is more stable? Obviously, this is more stable, and therefore this is the kinetic product, and this is also the thermodynamic product, which is the most stable product. So we cannot blindly assume that 1,4 addition product is always the thermodynamic product. A kinetic product can also be a more stable product. Here is one more example. We have 2,4-hexadiene, which is reacting with HCl to undergo an electrophilic addition reaction, in which case it is able to form two different products. One is a 1,2 addition product and the other one is a 1,4 addition product. Now, when we compare the stabilities of these two compounds right here, we can see that both of them are disubstituted alkenes and they're going to have pretty much the same stability. So here again, we cannot say that the 1,4 addition product is the thermodynamic product or the stable product.